In this talk, I will be presenting about our recent work on optimal probes for global quantum thermometry. The control and manipulation of quantum systems at ultra-low temperatures is key to quantum technologies across many platforms. For example, atomic gases can be cooled down to sub-nanokelvin regime. As such, it is crucial to have thermometers with high precision at very low temperatures. Quantum thermometry seeks to utilize quantum resources, such as coherence and entanglement, to improve the metrological capabilities of thermometers. Broadly speaking, thermometry protocols can be described in two main ways. Firstly, the conventional equilibrium approach, in which the probe is measured after reaching a thermal equilibrium with the system, and is described by thermal states with the same temperature as the system. Also, we have non-equilibrium methods which extract the temperature information as a parameter of the probe before the probe reaches a steady state. In many recent works, it has been shown that the non-equilibrium method can sometimes provide a higher precision as compared to its equilibrium counterpart. Nonetheless, in both cases, the uncertainty in the temperature satisfies the quantum Cramer-Round inequality, where m here refers to the number of measurement samples. The quantum Fisher information F sets a lower bound to the uncertainty. In this work, we restrict our discussion to just equilibrium thermometry. At thermal equilibrium, it turns out that the optimal measurement basis is the energy basis of the probe. The thermal quantum information is simply proportional to the heat capacity or the energy variance of the probe. To increase precision, one has to thus increase the quantum Fisher information. However, this depends on the actual energy spectrum of the probe. An interesting question then arises: what is the optimal Hamiltonian that maximizes the thermal quantum Fisher information? This question was answered in the previous work, where they proved that the optimal spectrum is an effective two-level system with a single ground state and an n-1-fold degenerate excited state. They also showed that the optimal energy gap epsilon here satisfies the following equation. Nonetheless, there are two serious limitations with these protocols. Firstly, from the equation, we see that the energy gap scales linearly with the temperature. However, the temperature is generally unknown to us. Thus, the probe cannot be optimized unless the temperature is already known within a narrow temperature range. Due to this limitation, we refer to this scheme as local thermometry. Moreover, this optimal probe requires enormous degeneracy in the excited state and is very difficult to be realized in practice. Based on this, there are several natural questions that one can ask. How can we design a probe which operates optimally over a wide range of temperatures? What does the optimal probe look like if one takes the practical constraints into account? We will address all of these aforementioned questions in this presentation. Let us first introduce the notion of global thermometry, in which the probe can operate optimally over a wide range of temperatures. We first define the average variance G over a temperature range between Tmin and Tmax, which is minimized numerically. The temperature estimation can also be done adaptively in the sense that once the temperature is estimated for a given range, then one can use a secondary probe optimized for a smaller range in order to get a better estimate. Here we show the optimal energy spectrum for 16 and 64 energy levels respectively, for a temperature range of up to 150 when we consider the ratio between Tmax and Tmin. Since the ground state is fixed to have zero energy, we only plot the excited states in this diagram, where Ek refers to the energy of the kth excited state. In the limiting case, where Tmax and Tmin are identical, it is unsurprising that we recover the local thermometry case. As the temperature range is increased further, the optimal solution is indeed, again, an effective two-level system with an n-1-fold degenerate excited state. We call this regime phase 1 thermometry. The energy gap here is described by a correction to the optimal conditions found for the local thermometry case. In both diagrams, the upper and lower dashed lines denote the optimal energy gap when the probe is optimized for only either Tmax or Tmin respectively. This gives a very nice physical intuition for the optimal energy gap as a compromise between the locally optimal probes at Tmax and Tmin. As the temperature ratio is increased beyond some critical ratio, the optimal energy spectrum is no longer an effective two-level system. Instead, the energy levels bifurcate into two branches, thus creating a new regime of energy spectrum, which we call phase 2 thermometry. The optimal probe in phase 2 is now an effective three-level system. The bifurcation of energy levels can be physically interpreted as the case where the optimal probe has to be sensitive to both ends of the temperature range. When the temperature range is small, optimizing the probe at a temperature near the average temperature of the range gives a sufficiently high quantum Fisher information at both ends of the range. The optimal solution is thus the highly degenerate effective two-level system, similar to the case of local thermometry. This argument is obviously not true in the limits where the temperature range is large, and the energy gaps have to be split up in order to produce an effective probe over the entire temperature range. The critical ratios where bifurcations occur are plotted against the number of energy levels. An interesting observation is that at n equals to 40, the critical ratio tau2 decreases sharply with the emergence of phase 4 as signified by the presence of tau3. In short, we have discovered new phases of optimal solutions for global quantum thermometry, where the previously found effective two-level system is no longer ideal. This allows us to separate quantum thermometry into various regimes. The optimal probes for global thermometry demand a special form of energy structure, which can be difficult to engineer with physical systems. Moreover, even if such spectra can be engineered, it might still be challenging to measure the probe in the energy basis, which is required to saturate the Kramer-Round bound. Hence, there is a need to design practical probes with a sufficiently precise performance as compared to the theoretical limits. To this end, let us consider a non-uniform XYZ Hamiltonian with the presence of local external magnetic fields in all three directions. The couplings and fields are also allowed to vary independently throughout the spin chain. This gives a non-uniform Heisenberg XXX Hamiltonian when we simplify X, Y, Z to be in the same magnitude. In practice, it is difficult to engineer exchange coupling with varying signs. Therefore, we must impose the constraint that the spin chain probe must either be antiferromagnetic or ferromagnetic, while the signs of the local magnetic fields can be arbitrarily varied. As before, we minimize the average variance over various Tmin and Tmax against the parameters in the XYZ Hamiltonian. Interestingly, the optimization yields the classical Ising model where Jx, Jy, Hx, and Hy are all zero. So the remaining direction is only in the Z direction. Now the figures here show the optimal Ising coupling and magnetic fields obtained from the XYZ Hamiltonian in the case of 4 spins. For thermometry in phase 1, it turns out that the optimal solution is a uniform ferromagnetic Ising model. And at the critical ratios indicated by the dashed lines, the uniformity of the parameters break down. And the parameters now show a more sophisticated pattern. For the XXX probe, the optimal probe in this case turns out to be a fully dimerized chain, where Ji is 0 for I even I and positive for odd I. In this case, we have presented the situation for 6 spins, where the optimal solution is now 3 independent dimers with J1, J2, and J3 decoupling between the dimers. In phase 1, the dimers are all identical to each other. Again, at the critical ratios depicted by the dashed line, the coupling parameter splits into multiple branches. It is also insightful to study the energy spectra of the optimized spin chain probes for both the XYZ Hamiltonian and the XXX Hamiltonian. For optimal probes of size n equals to 4 spins, we plot the energy spectra for Tmax over Tmin equals to 1, which corresponds to phase 1, and Tmax over Tmin equals to 5, which corresponds to phase 2, respectively. For phase 1, the Ising energy levels shown here are on average closer to the optimal energy E optimum, denoted by the dashed line. Likewise, considering the case of phase 2 thermometry, the Ising energy levels are again closer to the respective optimal energies E1 and E2. In particular, we see that the Ising model has a single first excited state very close to E1, whereas the first excited state of the dimer must be threefold degenerate. This suggests that the Ising probe performs better than the dimerized probe in both cases, which is not surprising since the XYZ Hamiltonian is more general than the XXX Hamiltonian. We can also compare their performance with the theoretically ideal thermometers. To do so, we compute the relative difference in G with the optimum G for probes with n equals to 4 spins over a range of Tmax over Tmin for which the two phases are observable. When G is small, this represents that the probe perform closer to the theoretical limits. Remarkably, the Ising and dimerized probes perform closer to the theoretical limit in phase 2 as compared to phase 1. In addition, the Ising probe indeed outperforms the dimerized probe at all values of Tmax over Tmin as expected. In summary, we have introduced the notion of global quantum thermometry and showed that the optimal solution differs from that of local thermometry. Interestingly, the optimum energy structure undergoes several phases where the energy levels bifurcate. The optimum solution can be approximated by realistic spin chains, where the best models were found to be the Ising model and the dimerized chain. The optimized parameters for the spin chains also exhibit phases of solutions. One another advantage of the Ising and dimer chains is that one can easily measure them in the energy basis, which is optimum for equilibrium thermometry. For example, energy measurements on the dimers can be achieved easily via singlet triplet measurements commonly used in quantum dot arrays. Our results open up new regimes of thermometry and address the key limitations of local thermometry. An interesting future work is to study global quantum thermometry in the non-equilibrium case. With that, I thank you for your attention.